independent variables that we have, we use this. We would see x1, x2, x3, x4, so on and so forth. The next one that we have is the statistical standard error. So which is this one, right? So this column essentially represents the statistical standard error for each of the coefficients, right? And what happens that if you have a good regression model, the standard error should be at least 5 to 10 times smaller than the corresponding coefficient, right? So a large ratio indicates that there is no significant variability in the slope estimate, right, which is B1, X1 here, and the ratio of the estimates to the standard error, right? So the ratio of this estimate to the standard error is referred to as your T statistic, right? This column right here. And the T statistic, right, is the value that is used to compute this column, right? The probability, that we get a T statistic greater than what we have here. And I'll explain that now, but the T statistic essentially is calculated by comparing the ratios of a T distribution with n-2 degrees of freedom. Okay, and then we have this probability that of observing a T value as extreme or more extreme as the observed, right? Assuming that the null hypothesis holds between the independent and dependent variables. And the null hypothesis in this scenario is that there is no linear relationship between the variables, right? So because our hypothesis is that there is a linear regression. There is a linear relationship, right? And as you can see that we have a probability of 0, so therefore, like, there is a linear relationship here in this scenario. So yeah, very small. Okay. Okay, and then the last two is the R squared, right? And this is a statistical, anyway, it's good there. So this statistical measure is used to measure how good the model describes the measured data, right? And it is within a range of 0 to 1. And as you can see here, we have like 11.19 or 11.9, right? 0.119, you can make that a percentage between 0 and 100, and that's like 11%. Right, so the R2 value is calculated by dividing the total variation explained by the model with the total variation in the measured data. All right, so values of R squared closer to 1 indicate a good model, and a good model does not necessarily need to have a large R squared value, and can actually be a good predictor, even if it has a small R2 value. So essentially, what they're saying is that 11.9% in the variation of our in the scenario, we're not doing salary packages, but 11% of the predicted outcome is represented by the total variation of what we're using as a predictor, right? So, and then we have adjusted R squared. Okay, we don't have that, but adjusted R squared is essentially, it takes into consideration the number of predictors used in the model, right? It's usually smaller than the R squared. Okay, and now this is another plot, the QQ quanti plot, and is used to check whether the regression residuals are normally distributed. And if they were normally distributed, they would follow this line. But as you can see here, we have a deviation at both ends, letting us know that that is not this, the errors is not normally distributed, right? So we can see here that, okay, this deviates from our normal line here to even like a greater degree than these ones. So then you would now have to go and start working on either, now you know that, okay, there's not a linear relationship, or residual plot is not normally distributed. All right, so okay, maybe this regression can be improved. Okay, so that is that. Now, how to determine the regression coefficients is what we'll get to now. Cool. And we'll just take that, see there. Okay, guys, so welcome to this demonstration on how you determine your B1 and B0, right? I will also show you the least squares method, right? So now, okay, so as you can see, this is our dependent variable, and our independent variable I've set to 0. So therefore, you see our regression estimate is the green one, which is just there. But now let's give it some values, right? Okay. Please make it a bit more. And as you can see, what happens is our regression line, this is our regression, right? And then this is our independent variables, our observations, the ones in the blue. And then our regression is shown in the green. But let me add a trend line to see how that works. There we go. Okay, so that is our fitted line, right? Based on this combination of independent variables and dependent variables and independent variables. And if you can see, this dark brown and red lines are what we use to determine our B1s or B1 or feature coefficient, right? So essentially what this line is, if I'm not mistaken, is our y average, okay? And our x average is 3. So our y average is the average of our independent variable, right? Which is 7.6, right? Okay. 7.6, and then we now see our x average is now 3, which is 3 over there, okay? And they intersect. Now, what is known is that your regression line will always pass through this point, right? As you can see over there. And now, to calculate that, right, we do this this math over here, right? So on column E, right, we're going to say for each dependent variable, right, for each observation, right, right, we want to take our dependent variable and subtract it from our x average. That way we have -2. So it's 1 minus 3 is -2. 2 minus 3 is -1. 3 minus 3 is 0. 4 minus 3 is 1. 5 minus 3 is 2. And then we do the same for our y's as well. Okay. 3 minus 7.6 is -4.6. 8 minus 7.6 is 0.4. 6 minus 7.6 is -1.6. 9 is 1.4. 12, and so on and so forth, right? And then we now say we want to get the square root of this into our x, right? So we square by 2, and we get these values. Then we also now want to get the product of these two columns over here, which we now get over there, okay? And we get that. From there, right, we use this formula here, right? Now, this formula is a representation of what I've done over here, right? And just border here as well. Okay, so now this formula says we're going to take the sum of this h, right? And then we're going to take the sum of this column, right? And divide it by the sum of this column, right? You see that there, sum of h2 minus sum of g2, okay? And that gives us our b coefficient, right? Now that we've calculated our b coefficient, how do we get the y-intercept, right? Remember from high school mathematics, we say y plus mx plus c, right? And in this scenario, we're trying to find c, and we have n, right? Which is our gradient, and which is 1.9. So we say, okay, well, we know that at what we're trying to find c, right? So at x is equals to what is y when x is equals to 0, essentially, and then we now find our intercept, right? Yeah, when x is equals to 0. Okay. So then we now have y is equals to x is equals to 0, y is equals to c, but we don't know what c is. So there's a way to do that. Let's escape my head right now. But so now that we found y is equals to, we found b1, right? So let me just show you how you now find b0. All right. So already have that thing. Yes. Yes. That is how you find y is equals to b0, right? So we know that our regression line is at this point. We know that it passes through the x average and y average, right? Yeah. So we can now say that we know that y is equals to this, is equals to 7.6, and x is equals to 3, right? And we try to find c. So we just do make c the subject of the formula, which is going to be, take this to the other side, which is going to be y minus mx, if I'm not mistaken. So if we look at that, it's going to be y minus mx, which is just 3 multiplied by this. And then that's how you get your your intercept. Okay, so now that I've explained that, let me now explain what the least squares does, right? So we move here. Okay, so I am going to put this on 0. Okay, so should I, let me see if I can move this a bit. Okay, ignore those hidden cells over there, but yeah, it's just formulas that can be removed. So what happens is now, so we have our observations, right? I don't know what, okay, yeah, why it's saying dependent variable, but that is why. So those are observations of our dependent variable given an independent variable. So this is that. And how I started this off is, so, we're trying to find, we're saying, okay, you know what, let us use the average line, right? The average of our observations, right? And that is, okay, we look at this, when we take the average, there it is, it should be 10.1, right? So we say, okay, look, the average, right? How good is it as a predictor, right? And then you can just zoom out a bit. Okay, then we just zoom out a bit. So look at our coefficient of determination, it's essentially 0. So it's saying, okay, what is a terrible plot? This is a terrible predictor, right? So what happens is in the regression, simple linear regression, essentially what we're trying to do is find the line that fits this data, right? And what that means is we're trying to reduce the sum of errors, right? Sum of squared errors, okay? So now you can see how big our error is here, 193, using our average line, and here the estimated line is essentially the average, right? Just a bit, estimate the value. Why do I have to estimate the values? But okay, cool. Maybe I should put this in. Okay, so now let's say I increase this by 10. Okay, so you see my sum of squared errors is reduced. That's okay, cool. Let me reduce that. Let me increase that again. Then I see there's my sum is reducing. Sum of errors is reducing. So we're trying to minimize our sum of errors, right? And you can see my R squared is increasing. So you're saying, okay, cool, that's getting better. Oh, it's increasing again, that's getting better. That's getting better. Let's see, how good can we get it? It's getting better. Getting worse. As you can see now from there, we had a good fit. So between 60 and 70 degrees of rotation, we lost our optimal value. So increase that. Then you see this now, okay, we're now doing bad. So essentially, this is how linear regression works. We're trying to minimize the sum of our residuals there. So you see, it's somewhere in between there. So let me just start playing with it over here. I can say 61. There was an increase. Ooh, no. 62. Now, I guess 61 and 63, there was a reduction. Let's see if there's a reduction again. There's a reduction again. There's a reduction. Okay, so what did I do? Page up. So there's if we go back to 60, it's 0.7578. And then if we go to if we go to 61, there's an increase there. And then 62, there's a decrease. So our value is 61. Okay, so that's our fitted regression line. And then you could now find the V1. So for this problem, some of these squares. Okay, so this is just a demonstration of how linear regression works. In the next video, we will go through a scenario where we use Python and we do a problem of trying to use linear regression to calculate or determine the price of an Uber or Lyft trip. All right, see you guys then. Cheers.